Okay guys, so in the last video we have said that the GPO pins when IO of enable is 1, that means it can act in two mode, SPI mode also, ART mode also. So first of all, in this video we are going to talk about the serial IO and SPIO mode. Okay, first let us talk about what do we mean by parallel IO and what do we mean by serial IO. In parallel IO, what happens is that many wires are there at once. MCU sending 8 bits at once. See, MCU is sending 8 bits at one to the device. So 8 wires are there and 8 bits are sent at the same time. It's fast, but it needs many wires. But if you see serial IO, one wire is there and bit by one, a single wire is there between MCU and device. You can see. And MCU is sending 8 bits one by one. It is slower but needs only one wire. So this is the difference between parallel versus serial IO. So in parallel IO, MCU, that is our microcontroller unit, can send 8 bits if it want to send. It can send at once by using 8 wires, right? So 8 bit can be sent parallelly at the same time to the device. It is fast, but the problem here in parallel IO is that it needs a lot of wires. Now here if you see, on the case of serial IO, there is only one wire and only after one bit and one bit after other, like that only you can basically send the bits to the device. Microcontroller unit can send it to the device only like this. So you have to understand that the serial IO is what? The serial IO is basically slower, but it needs only one wire. Okay. First, we have understood what is the difference between the serial IO and the parallel IO, right? So this is just a real life analogy which you don't need to understand. I hope you have understood what do we mean by serial and parallel IO. Here if you see, serial is popular. So first I want you to understand the difference between the serial IO and the parallel IO. Okay. Now here if you see, serial is popular, mostly used, because the problem with the parallel is that 8 bits we need 8 pins used. 16 bits 16 pins is needed. 13 bits 32 pins is used. MCU but only have 19 GPIO pins. Pin can run out. But here for 8 bits, 16 bits, 32 bit and all, one pin is used in serial. So therefore it saves pin. So why the serial is popular here? That is the next thing that you have to understand. So the serial is popular here because here problem when we are talking about, the problem comes with parallel is that how many bits you have to transfer. Like MCU has only 19 GPIO pins, we know that. So for 8 bits, or if you're considering 16 bits, 32 bits and all, you need 8 pins, 16 pins, 32 pins and all needed. So that is a problem. So pin can run out very quickly there. So the solution here is serial, because whatever be the number of bits, only one pin can be used here. So it can save the pin for other users also. So that is why we have said the solution here would be the serial, because in the serial case only for whether it be 8 bits, whether it be 16 bits, whether it be 32 bits, only one pin is needed there. Now let's see serial standard. Think of standards like languages. If MCU speak English and sensors speak French, they can't communicate, right? So standards make sure everyone would speak the same language. So common serial standards are there. Some standards are there which would make sure that MCU and the sensor, what will be the device, can speak the same language. So for that we have this common serial standards like SPI, UART, 12C, I2C, right, I2C, USB, Ethernet are the different serial standards which is basically there. So SPI is fast, simple and short range. UART is simple but no clock wire. We will understand what do we mean by SPI and UART in detail. I2C, many devices, 2 wires only. USB, your phone charger cable is USB. Ethernet is the internet cable. So there are common serial standards, because if MCU is speaking different language and the sensor, let's say device, is speaking different language, how can they communicate? They cannot communicate. So there is a standard, the standard for communication. a common serial standards are there which make sure that everyone would speak the same language. These are UART, SPI, I2C, Ethernet, USB, and all. These are the different example of the common serial standards which is basically used. Now here we are going to understand in this video SPI in detail. SPI is not a serial peripheral interface. Serial means one bit at a time. Peripheral, it is connected to the external device. Interface is like a way of communication. So MCU can communicate, microcontroller unit can communicate with this external device using this SPI, that is serial peripheral interface. Okay, so this is how we are going to spell, how you pronounce SPI, like SPI, that's it. Okay, now SPI is synchronous, means this SPI is actually communicating on the basis of clock. There is a clock wire. Okay, SPI is synchronous means there is a clock wire and both devices would follow the same clock beat, like MCU and the external device, like two people clapping together in that is synchronous. Asynchronous means there is no clock wire, devices agree on speed beforehand. It's like not, there is on the basis of clock, if the clock beat, the devices are following this clock beat, then it is synchronous. So here we have to understand the SPI, serial peripheral interface, is actually synchronous. So what did I mean by saying it's synchronous? It is synchronous means it has a clock wire. That is what you have to understand. There is a clock wire and the devices follow according to this clock beat. That is what you have to understand. Devices are following according to the clock beat. Understood? So this much we have understood about our SPI. Did I say CPI a lot of time? Maybe. I'm so sorry about that. It's SPI, okay? Serial peripheral interface, okay? So SPI is synchronous, that is there is a clock wire here, and also there is a both devices is following the same clock beat also here. Understood? Now there are some SPI pins. The three wires, that is our microcontroller unit has to communicate with this peripheral device, I told you, using SPI. Now SPI has three wires, that is SCK, SDO and SDI. See, SCK is serial, the clock. We told you there is a clock wire. Serial clock is SCK, which is direction is from the MCU to device, and its heartbeat keeps both in sync. That is what this SCK do. It's like the serial clock that actually make sure this MCU and peripheral is in a sync, like synchronous, right? Both of these devices are basically following the same clock beat that is maintained by this from MCU to peripheral devices. Now SDO is the serial data out. That means from MCU to device, MCU sends some data to the device, that is serial data out. Now serial data in means from the device to the MCU it is coming. MCU would receive from some data from the peripheral device. So there are basically three wires in our SPI pin that you have to understand. SC7 is the clock from MCU to peripheral device. Then SDO is also there, SDI also there. SDO is a serial data output and SDI is serial data input. Serial data output means from the MCU you are giving it to the peripheral device. Serial, not output, serial data out and serial data in. You are giving to the peripheral devices serial data out, and from the peripheral device you are getting it to the MCU. This is serial data in. Okay, so this is the three important wires that is there in our SPI pins. Understood? This you have to understand. Now I told you how. Now we have to understand how this SPI actually works. So there is one diagram there that I have to take from my notes. This is the KTU notes that you can download it from the site. So now here if you see, you can see this diagram. This is the diagram of our SPI configuration. Fine. We will understand this diagram here. First that we have to understand how the SPI actually works. Here if you see how SPI works, here we will send 8 bit of data. Step 1 is what? MCU is starting the clock, SCK. SCK is the clock. So let's say we are sending 8 bits of data. That is our thing that we're going to do, and that we are going to see step by step. Step 1 is MCU starting the clock. 8 clock pulses would be there for 8 bits of data. Fine. Now MCU sends bits on how? From the MCU, I'm giving the data, I'm sending 8 bit of data to the peripheral device. So at each clock pulse, one bit will be sent. Clock pulse 1, send bit 1. Clock pulse 2, send bit 2, like that. Send the last bit at clock, least significant bit at clock plus 8. And step 3 is that device is responding to this, this device would respond on what? This SDI. That is, at the same time, device can send its own data back to MCI also. Device can respond also to this data using the serial data in. Okay, so this you have to understand. So here if you see, at the falling edge, the bit would, rising edge is there, falling edge is there for each clock pulse. So falling edge bit changes, new bit placed on the wire. Rising edge bit is sampled, read or captured. So falling edge, in the falling edge the bit would be placed, and the rising edge is when this bit can be captured. Bit is read. Understood? So during the falling edge, like falling edge is like I am, like if I consider mailbox, in the falling edge I will place the letter in the mailbox, and I am reading that letter in the rising edge. Understood? So that is what happened. I am capturing or reading the bit in the rising edge, right? Then only I can send that bit to the device. Device can respond on what? SDI. That is the our data in part, right? So here if you see, you have the rising edge and the falling edge. Rising edge means bit is captured in the rising edge. Falling edge means that the bit basically changes here. That is, the new bit is coming to the wire in the falling edge. Fine. Now let's understand about the chip enable concept. Sometimes MCU is connected to multiple devices. Most of the time MCU is connected to multiple devices. So the problem is that both devices share same wires. How does the MCU say, hey, I am talking to you specially? That is using the chip enable. That is, if chip enable is low means, hey, you wake up, data is coming. Chip enable is 1 means not you, you go back to sleep. Okay. So called active low because 0 means on and 1 means off. So each of these devices have a chip enable pin. It is actually called as active when it is low, because when the chip enable is 0, that only means that this device has to wake up, and I am sending data to this MCU, sending data to that device 1. And if chip enable of any device is 1 means you can just sit there like that, you can go back to sleep. That is what that means. You don't need to send the data. Here MCU is not sending the data here. But when the chip enable is 0, it's like active low. That is why it is called as active low, because it's active in the low condition. When the chip enable is 0 means only that device we will send the data, MCU is sending the data. So this chip enable is why we are using is like it's a doorbell. It acts like a doorbell. The chip enable is used because when our MCU is connected to multiple devices, it has to know, like you can say MCU is connected to multiple devices, so it has to know which device we are basically talking to. So each of these devices has a chip enable, and chip enable is an active low pin because it is active only when the chip enable is 0. When it is 0 only, that MCU is telling this device that you should wake up, the data is coming. But if chip enable is 1 means MCU is telling to this device that you should not wake up, you can just go back to sleep, I am not talking to you. Okay, that is what it means. So here you have to understand chip enable is an active low case. Okay, so the full SPI communication, how, let us see. MCU, let's say MCU wanted to send this bits to the device. Now it has 1, 2, 3, 4, 5, 6, 7, 8 bits. So initially, first what I am going to do, I am going to set the chip enable. Chip enable, I have to set active low. Then only I can, for this device, I want to set the chip enable to be low. Now clock is set. Now at each bits rising edge, what we are going to do is that at each bits falling edge we will put that data in there, and rising edge we will send that data to the device. That is what we will do. SDO O, and SDI is the response from the device. Fine. So this is the summary of serial IO. Means there are parallel IO and serial IO. Parallel IO means many wires are required. So in mostly famous is the serial IO, because if there are, because our we know in our case we have only 19 GPIO pins, so serial IO is mostly used. And the most communication, as I told you here, there are communication, for the communication purpose we have common serial standards between the MCU and the external device. We have said that we will use serial standards, but now what are the different serial communication things that we do? We have SPI, UART, I2C, USB and Ethernet. From there we were talking about SPI, that is serial peripheral interface, and in SPI we have told that it is synchronous. It is like that it will maintain SCK would, there are three wires, right? SCK, SDO and SDI. SCK would maintain the two devices in a sync, and also a chip enabled pin is also there to select which device. SCK is the clock. We know SDO is MCU sending data out. SDI means MCU is receiving the data. Now bit would change in the falling edge, and bit is red on the rising edge. MCA first sent what, the most significant bit, then it will later send the least significant bit. That is, you have to understand most significant bit here. One example was there. This first you will be sending the most significant bit, like what is the most significant bit here? Most significant bit will be given first, like 1 0 1 0. Most significant bit would be given first, then only the last we will send the least significant bit. Okay, so here you can see between our peripheral device and MCU micro unit controller we have this SCK, SDO, and SDO means what? From this you are writing to here. Okay, and SDI means what? From here you are going to here, from peripheral device. So here this would act as SDI. Why? Because it is receiving the input. Now this means what? From here it is coming to here, right? Now this means what? Output here. Then chip enable is there in this peripheral devices. Peripheral devices that has this chip enable, and SPI, that is SPI also there is a chip enable in SPI, that is complement because it is active low, right? The opposite is the active condition, 0 is the active. That is why we have taken a complement case here. If you see here, SCK, SDO means from the controller to peripheral device, SDI means from the peripheral device to the controller. But here SDI means what? Here SDI means peripheral device. If in the controller it is SDO, then the peripheral device would act as SDI. Now if my controller is SDI, that means then my peripheral device would act as what? SDO, like opposite, right? Now SPO control enable, chip enable is also there, and peripheral device also has a chip enable. The direction is this. Okay, now it's complement because we are taking the active low case. Now we have SCK signal, and each of these SDO means what? We are writing it to the chip. At each of this rising edge you can see we are sending bit 7, bit 6, bit 5, bit 4, bit 3, bit 2, bit 1 and bit 0. Understood? And SDO, peripheral device SDO means what? From here to here, peripheral device. SDO of the controller is like this, and SDO of the peripheral device, and it is active low. SPI is chip enable is active low, that is full low. Fine, it is full low here. This is how the SDO bits are being transferred, and this is in the controller case, and in the peripheral device case this is how the SPI bits are basically getting traveled. Means how from the peripheral device it is going to the controller like this, and like this would be how from the controller it is going to the peripheral device. Fine. So this is about SPI.